Years after the Spanish-American War, U.S. Admiral George Dewey made a surprising admission. He stated that if the opposing fleet fielded a single functioning submarine, he wouldn't have been able to sustain his blockade for even 24 hours. In 1885, that kind of naval threat was almost unimaginable. The oceans were entirely dominated by massive, vulnerable steamships and wind-powered vessels that were confined entirely to the surface. But Spain's vast overseas empire was increasingly exposed to foreign aggression. When a German gunboat sailed up to the Spanish-owned Caroline Islands and raised a flag, it laid bare a severe military vulnerability. Desperate for a strategic equalizer, the Spanish government agreed to fund a radical proposal from an engineer named Isaac Peral. He wanted to build an electric military submarine, a sharp departure from the crude, human-powered novelties of the time. To actually make an underwater warship viable, Peral had to solve three strict physical limitations of the ocean. First, propulsion. You can't run a standard combustion engine or steam boiler underwater without a constant supply of surface air. Second, buoyancy. An enclosed metal cylinder doesn't naturally hover in the water column. It wants to either bob uncontrollably to the surface or crash heavily into the seabed. And third, combat capability. If you are entirely submerged in a steel tube, you are effectively blind, making it nearly impossible to locate targets or fire a weapon without sinking yourself. Peral recognized that lead-acid batteries, advanced electric motors, and self-propelled torpedoes were all emerging at the same time, creating the ingredients for a vessel that could finally operate beneath the waves. His answer to the propulsion problem was a massive 30-metric-ton bank of 613 lead-acid battery cells, which occupied more interior space than any other component on the ship. That electrical grid fed directly into two 22-kilowatt electric motors at the stern. To maximize their efficiency, Peral connected them to a reduction gear system, stepping the output down at a 3-to-1 ratio before delivering the torque to the propeller shafts. That same electrical supply also powered an onboard piston air compressor. Its primary job was to pack air into large storage tanks, which could be released to regenerate a breathable atmosphere for the sailors inside. That pneumatic system was so robust, Peral even used it to solve sanitation. The submarine featured a pneumatic toilet that actively utilized high-pressure air to eject waste out of the hull, directly against the immense pressure of the surrounding sea. By fully committing to a closed-loop electric and pneumatic power grid, Peral severed the submarine's reliance on the surface, achieving true autonomous propulsion. With propulsion solved, Peral faced the buoyancy problem. Maintaining a level depth while moving underwater is notoriously difficult, and manual human reflexes simply aren't fast enough to correct a heavy steel ship before it breaches or dives too deep. To keep the vessel stable, Peral invented an automated mechanical brain, a highly classified depth control device. It relied on two key inputs. The first was a hydrostat, built around a flattened sinusoidal tube. As the submarine descended and outside water pressure increased, this tube would physically stretch outward along a set of tracks. But depth alone isn't enough. You also need pitch, so the second input was a suspended pendulum that swung back and forth, sensing exactly when the nose of the submarine tilted upward or downward. A series of mechanical rods continuously combined the stretching of the tube with the swing of the pendulum. As those two variables shifted, the rods triggered an electrical contact plate, automatically spinning up the forward or aft depth propellers to instantly level out the ship. What Peral built was an early, fully mechanical version of proportional derivative control. He was calculating the complex mathematics of automated navigation decades before the invention of modern computers. Finally, to fight blind, the crew needed a way to see past their steel walls. Peral designed a fixed optical periscope topped with a prismatic lantern. When raised just above the waterline, a reflective element inside captured the surface view and projected the image down a tube, directly into the command center. By adjusting an optical table beneath that projection to bring the image into focus, the crew could accurately estimate distance and calculate firing solutions for their targets without exposing the hull. Once locked on, they initiated a careful firing sequence. With water tightly sealed behind inner doors, they opened the outer tube and released a violent burst of compressed air, forcing a 280-kilogram bronze Schwarzkopf torpedo out into the ocean. These combined systems allowed the crew to locate and engage enemy ships from beneath the surface without ever needing to expose the hull to defensive fire. During sea trials in 1888, the machine performed exactly as designed. It successfully navigated underwater, maintained a controlled depth, and launched its torpedoes without error. Yet, despite proving the impossible, the project stalled. Facing severe political opposition and deep skepticism within the Spanish Naval Command, the submarine was quietly withdrawn from service and placed into storage in 1890. 8 years later, Spain went to war with the United States. Without a single submarine in the water, the Spanish fleet was decisively destroyed. The Peral submarine was eventually ordered to be scrapped, but the demolition never happened. Today, the intact steel hull sits preserved outside a naval museum in Spain. Isaac Peral's design proved to be decades ahead of its time. Its legacy was finally codified in 2023, when the Spanish Navy commissioned a new class of advanced attack submarines, the first of which was named for Peral himself.